Typically, weekly sales will drop off rather quickly after the end of an advertising campaign. This drop in sales is known as sales decay. Suppose that the gross sales, S, in hundreds of dollars of a certain product is given by the exponential function. S of t equals 2,000 times 2 to the negative 0.8t, where t is the number of weeks after the end of the campaign. And we want to answer the following questions. This is our first question. What is the level of sales immediately after the end of the ad campaign when t equals 0? So what we have in this function is an exponential function because our variable is in the exponent. And we want to evaluate this function at a value of t equals 0. We're going to substitute a 0 in for the value of t, giving us 2,000 times 2 to the negative 0.8t, and that t is 0. So that's going to give 2,000 times 2 to the 0 power, because negative 0.8 times 0 is 0, and 2 to the 0 power is 1. So we get 2,000 as the level of sales immediately following the campaign. I just want to make a note here that this S is given in hundreds of dollars. So it's not $2,000. It is 2,000 in terms of hundreds. So that sales is actually $200,000. So because this is in hundreds of dollars, the actual dollars is 200,000. So in your homework, though, we will type the 2,000. We just have to keep in mind that those units in real dollars are something different. In part B, we want to know what the level of sales 1 week after the end of the advertising campaign. So that means that our time that has passed is 1 week. We notice that if we go back to the original problem, t is given in the number of weeks. So 1 week later, the value of t will be 1. We want to find S of 1. That will be 2,000 times 2 to the negative 0.8 times 1. And that's 2,000 times 2 to the negative 0.8. We're going to use a calculator to work this out. So in my calculator, I'm going to type 2,000 times 2 to the negative 0.8 power, and we get 1,148. And I'm going to round to the nearest whole number, so that's 1,149. So this is in hundreds of dollars. So if we turn that into dollars, we're going to add 2 zeros. But in your homework, we are going to use the units that they were giving to us. In part C, the question is, what is the level of sales 5 weeks after the end of the advertising campaign? So that would have t equals 5 for 5 weeks. We're going to find S of 5. That's 2,000 times 2 to the negative 0.8 times 5. And let's type this in the calculator to get our answer. We're going to do 2,000 times 2 to the negative 0.8 times 5 to get 125. So you can see that the sales are dropping off. So this is in hundreds of dollars. So we get $12,500 in sales after 5 weeks. For this question, we want to use the periodic compound interest formula, which is given here. We'll go over that in just a second. And the question is, how much money will you have in 10 years if you invest $3,000 at 4.5% annual rate of interest, compounded quarterly? And how much will you have if it's compounded monthly? So let's take a look at this formula that we're working with. This is a periodic compound interest formula, and it's used to calculate how much money you'll have in an account that pays interest. So this formula is A equals P times 1 plus R over N raised to the NT. I want to take a moment to go through the different variables in the formula. We have P, which stands for principal, or your initial investment. So P is your beginning amount of money. R is the annual interest rate. N is the number of compoundings in 1 year. T is time in years. And A is the accrued amount. Now, some people are confused about this value of N. Basically, what it means is how often interest is added into the account. If you have a typical savings account, your interest is added into the account every month. And so that would mean that if every month you get interest added, that would be 12 times a year. So N would be 12. And that's what we're going to use in this part of the problem here. Interest is compounded monthly, and N will be 12. But this question also says that interest is compounded quarterly, and quarterly would be 4 times a year. So we're going to do this calculation 2 times, 1 for interest compounded monthly and 1 for interest compounded quarterly. So let's take a moment to go through the problem and identify what the given information is. It says, how much money will you have in 10 years? In 10 years, that is a time. That's how much time has passed. So T will equal 10. If you invest $3,000, that is our initial investment, our beginning amount of money, and that will be our principal. So P is equal to 3,000. This $3,000 is invested at an interest rate of 4.5%, 4.5% annual interest rate. So R is equal to 4.5%. However, when we use this value in the formula, we want to use it in its decimal form and not its percent form. So we're going to move that decimal place 2 places to the left, getting us 0.045. And then, as I mentioned earlier, it says here that interest will be compounded quarterly and compounded monthly. So we have two questions. Interest will be compounded quarterly 4 times a year, and then we'll do the calculation again for monthly 12 times a year. And at the beginning of the problem it says, how much money will you have? This is how much money you are accruing with your initial investment and the interest. So this A is what we're trying to solve for in the problem. So we're going to substitute the values into the formula. We have A equals P times 1 plus R over N to the NT. And that would give 3,000 times 1 plus 0.045 over N. So remember that N, we're going to do the calculation twice. For N equals 4, that's for quarterly. We have N, which is 4 times our time of 10 years. So this is our calculation for quarterly. And let me get my calculator out. Now, this calculator is going to allow me to type the entire expression at once. 3,000 times 1 plus 0.045 over 4 raised to the 4 times 10. And we've got, after 10 years, your account will grow to $4,693.13. Now, I want to show how we can calculate this if you have sort of a less advanced calculator. So if you don't have a calculator where you can type the whole thing at once, what I'm going to do is follow order of operations. So I'm going to do the operation inside the parenthesis first, and I'm going to do the division before the addition. I apply the exponent before I do the multiplication. So here is what I would do. 0.045 divided by 4. And I'm going to add 1 to the answer. Now I need to apply the exponent. My exponent is 4 times 10, which is 40, so I'm going to raise this to the 40th and then multiply by 3,000. And so you can see we get the same answer, the same accrued amount, by typing the whole formula or by following that order of operations. So then I will do the second calculation, which is the monthly calculation. So our formula would look like this. A equals 3,000 times 1 plus 0.045 divided by 12. This is the value of N. Another N times 10. So this is for the monthly calculation. And let's get our calculator again. And we're going to type 3,000 times 1 plus 0.045 over 12 to the 12 times 10. And after 10 years, if interest is compounded monthly, we're going to have a little bit more money. So that's interesting. If you add interest more often, your money grows a little bit faster. So we have 4,700, and if we round, 98 cents. An original investment of $6,000 earns 6% interest compounded continuously. will the investment be worth in 1 year and then in 10 years? I want to point out a key word for you here, that the interest is compounded continuously. So we're going to be using a compound interest formula, but it's a little bit different because instead of being compounded at these discrete moments, we are going to be compounding interest continuously, meaning that the interest gets added into your account all the time instead of at those discrete moments. So we have a different formula, which is A equals P e to the RT. And let's go over the different components of this formula, and you'll notice that these are the same components that we saw in the periodic compound interest formula. We have P, which is the principal or the initial investment. R is the annual interest rate. T is time. And A is the accrued amount, how much money we have after that period of time. You will notice that we have this E in the formula, and the E is not a variable, it is a constant, and E is approximately 2.718. But most of you, if you look on your calculator, will find that you do have a button for E, so you won't have to use this. You won't have to type 2.718. You'll be typing E in place of that formula. So this E comes about from the expression 1 plus 1 over n to the n. If you allow n to get larger and larger, then this expression approaches that value of 2.718. So what actually happened here is that the periodic formula was A equals P times 1 plus 1 R over N to the NT. And you can kind of see this formula here contains the expression involved in E. N was the number of compoundings. And as I said here, when our interest is compounded continuously, we're allowing those number of compoundings to become more frequent. We're allowing n to approach infinity. And so our formula for periodic compound interest simplified to this formula, A equals P e to the RT, by allowing that n to go to infinity. So let's read through our problem and find the different values for the variables. An original investment of $6,000, that is our principal. Our initial investment of $6,000 will earn 6% interest. R is 6%. And we're going to use the decimal version of that, so 0.06. Our time, we're given 2 time periods. We want to know how much that $6,000 grows to after 1 year and after 10 years. So we're going to do the calculation twice, once for 10 years and then again for 1 year. And we want to know what will the investment be worth. That's going to be our accrued amount. So A is what we're looking to calculate in this problem. We have A equals P e to the RT. If we substitute our values into the formula, we have $6,000 and our interest rate 0.06 and for a time period of 1 year. So this is our calculation for the 1 year time period. We're going to substitute that into our calculator. We'll do $6,000. And we want to find that E button on our calculator. For this calculator, it shows up in two different places. You've got the division symbol, and in blue above that division symbol we have E, and that is the E in the formula. And then on this button here, this is the LN button. In blue above it we have E to the X. So since we're going to be typing an exponent on our E, I'll use this one here. So it will type the E as well as get me ready for the exponent. I'll do second, the LN button, so you can see that it typed E with an exponent. And in the exponent, I'll type 0.06 times 1. So after 1 year, that $6,000 will grow to $6,371. And I should get the cents. If I round to the nearest cent, it would be 2 cents. So then we want to do the calculation again for 10 years. That would be A equals 6,000 times E to the 0.06 times 10. And let's type that in our calculator. We have 6,000 E to the 0.06 times 10. And that $6,000 will grow to be $10,932.71. The population of a rural city follows the exponential growth model. P of t equals 1,900 e to the 0.041 t, where t is the number of years after 1996. What is the population of this city in 1996? What is the relative growth rate as a percent? And we want to use this model to approximate the population in 2038. So before we really dive into these parts, I wanted to show you the typical format for a population growth and decay model. It mentions up here that this model is an exponential growth model. The growth model is when the city is growing in population. Decay model is if it were decaying or getting smaller. So the typical growth model and decay model will follow this form: P of t equals P naught e to the kt. And this looks really, really similar to another formula that's been discussed recently, and that was our continuous compound interest formula. So I'm just going to write this up here because I like to relate it to that formula. A equals P times E to the RT. So when we were talking about the continuous compound interest formula, this P stood for principal, which was our initial amount of money. And you'll notice in the same position in the formula, this P naught says initial amount. Now we're talking about the population, so this is going to be initial population. And then we have this K in the formula, and in that same position we have the R from the continuous compound interest formula. So if you remember, in that continuous compound interest formula, the R stood for the annual interest rate. So in our population growth model, that K is going to be our growth rate, or if your population is decaying, decay rate. And then our final variable here is our T, and that stood for time in years when we had the continuous compound interest formula. And here we have a time as well, but we don't have a restriction on years. It can be any unit of time. You just want to be consistent with your problem. And then I guess there is one more thing, this P. This is going to be the population after some period of time. So that's what we see on the other side. Over here, that would have been the accrued amount, how much money we had after time. This is going to be how much population we have after time. So if we compare the model that they gave us with the formula, the pattern for population growth and decay, we're going to be able to identify these different parts. So the formula is P of T equals P naught e to the KT, and the model that they gave us is P of T equals 1,900 e to the 0.041 t. So by matching these positions, we can see that P naught is the 1,900. We can see that the K is the 0.041. And we have, of course, the T's matching up with each other. So reading this model in a little bit more detail here, it says that T is the number of years after 1996. So this is when our model begins. That is our initial time and our initial population. So in this first question, it says, what is the population of the city in 1996? This model begins in 1996. So this is asking for what is P naught? What is the initial population? Now there are two different ways we can get this answer. You can notice that the 1,900 is in that position of P naught and answer it that way. P naught is 1,900, or you could recognize that 1996 is 0 years after 1996, and we can substitute a 0 into this model. That would give 1,900 e to the 0.041 times 0, and 0.041 times 0 will be 0, so we have e to the 0. E to the 0 is 1, and so we get 1,900 for the population in 1996. That's our answer for part A. For part B, what is the relative growth rate? The growth rate will be the value of K. So we have K equaling 0.041, and if we pay attention to the details, this question is asking for it to be written as a percent. So we're going to move that decimal place 2 places to the right to write 4.1% as the growth rate. And in our final part, it says to use this model to approximate the population in 2038. So to do that, we need to know how much time has passed. Notice that the variable in our model is time. And so in order to use the model, we need to know the value of time. So our time how much time has passed since 1996 would be 2038 minus 1996. And let's work out how much time that is. I think is that 42? Just going to double check with my calculator. Yes, 42 years have passed. And we'll substitute that into our model. P of 42 would be 1,900 times e to the 0.041 times 42. And let's get our calculator to work that out. So we're going to type 1,900 e to the 0.041 times 42. And after those 42 years, the population has grown from 1,900 to 10,632, if I round. 10,632. In 1975, a wildlife resource management team introduced a certain rabbit species into a forest for the first time. In 2006, the rabbit population had grown to 7,619. The relative growth rate for this rabbit species is 20%. Use the exponential growth model, P of t equals P naught e to the kt to answer the following. How many rabbits did the Wildlife Resource Management Team introduce into the forest in 1975? And how many rabbits can be expected in the year 2029? So this model, P of t equals P naught e to the kt, is used to model the rabbit's population. And those rabbits were introduced into the wild in 1975. And so this will act as our initial time, our year 0. Then in 2006, we have recorded, so how many years after? That would be 2006 minus 1975. That's 31 years later. It was recorded that that rabbit population had grown to 7,619. And the first part of this question says, how many rabbits did the Wildlife Resource Management Team introduce into the forest in 1975? So that would be our initial population, and that is unknown to us. So if I'm looking at this problem, I'm noticing that P naught is my missing information. I do know the relative growth rate. It's been given to me right here. 20% is the growth rate. So K will equal 20%, and written as a decimal, that would be 0.2. The time has been given to us, 31 years later. And we also know that the population has grown to 7,619. So I know all the variables in this equation except for the one that I'm looking for. So I can set up this equation as 7,619 equals P naught, which I don't know, e to the 0.2 times a time of 31 years. And I can solve this equation by dividing both sides by e to the 0.2 times 31. And I'm going to type that in my calculator to get P naught equals 7,619 divided by e to the 0.2 times 31. So that gives, by round, 15 rabbits. So the population started with 15 rabbits. And then in part B, we want to know how many rabbits are expected in the year 2029. So because I know the initial population, I can now use that in my model. And my model becomes P of t equals 15 times e to the 0.2 times t. And I only need to know the value of t to be able to use this model. So it's going to be 2029 minus 1975. So how many years since 1975? It's 54 years later. What is our rabbit population growing to? P of 54 is 15 times e to the 0.2 times 54. We'll type that into our model, into our calculator. 15 times e to the 0.2 times 54 gives us, oh, that's really big, 735,312 rabbits expected in 2029. 735,312. If I round to the nearest rabbit. Sketch the graph of the exponential function f of x equals 4 to the x. And we're going to make a table of values to find ordered pairs and then sketch the graph on this coordinate plane here. I'm going to use a standard set of x's, -2, -1, 0, 1, and 2. We're going to substitute these into our x. I'm going to start with the easy ones down here. 4 to the first power is 4. That would give the ordered pair 1, 4. 4 squared is 16, and that gives the ordered pair 2, 16. We have 4 to the 0 power, and 4 to the 0 power is 1. We get the ordered pair 0, 1. And we have 4 to the -1 power. And when we have a negative in the exponent, we can apply that by doing the reciprocal of the base. So we can write this as 1/4 to the first power. So that applied the negative. Applying the negative changed the base from 4 to 1/4, and 1/4 to the first power is 1/4. We get the ordered pair -1 and 1/4. Then we have 4 to the -2. I'm going to apply the negative by changing the base to the reciprocal, and then 1/4 squared is 1/16. So that gives the ordered pair -2 and 1/16. So this gives some ordered pairs. We're going to plot those ordered pairs. I have -2 and 1/16, so very, very close to the x-axis there. -1 and a fourth, pretty close, but not as close. 0, 1, and 1, 4, and 2, 16. 16 sort of goes off my grid a little bit. And we can sketch this by connecting these points together. You can see that in this direction our y is going off to infinity, and in this direction our y will get closer and closer and closer to the x-axis without ever reaching it. That means that this exponential function has a horizontal asymptote at y equals 0. On this end of the graph, x is going to negative infinity and y is approaching 0. Use the graph of y equals 3 to the x and transformations to sketch the exponential function f of x equals -3 to the x minus 5. Determine the domain and range. Also determine the y-intercept and find the equation of the horizontal asymptote. So we're going to start by taking a look at the graph of y equals 3 to the x. So I'm going to plot points to get those points on the graph. I'm going to choose a standard set, -2, -1, 0, 1, and 2. If I substitute that into 3 to the x, I'm going to get 3 to the -2, 3 to the -1, 3 to the 0, 3 to the 1, 3 squared. If we simplify, 3 squared is 9. 3 to the first is 3. 3 to the 0 is 1. 3 to the -1 is a third. 3 to the -2 is a ninth. So that gives us this set of ordered pairs to start with. I can plot them on my graph to get an idea of what the picture looks like. We have -2 and a ninth, -1 and a third, 0, 1, 1, 3, and 2, 9. And we can see that we have this nice exponential curve here. Going along the x-axis, we do have a horizontal asymptote, and that is at y equals 0. Now this is the graph of y equals 3 to the x. We want to graph -3 to the x minus 5. So we're going to use our knowledge about transformations to graph that. So we want to graph f of x equals -3 to the x minus 5. Now I'm not sure if it's minus or plus, so let me just double check. That is a minus 5. Okay. So our base function is the one that we just graphed, y equals 3 to the x. And we have two transformations that are going on here, this negative and also the minus 5. The negative is being multiplied, which with my knowledge of transformations tells me that this graph has a reflection. That negative is multiplied on the outside, so that's a vertical reflection. And the minus 5 is going to be a shift. Okay, all adding and subtracting gives us a shift. And because it's on the inside of the exponent, I know it's a horizontal shift. And because it is a minus, we're going to shift to the right 5. So my transformations are going to change the points on the original graph of 3 to the x. The vertical reflection, the vertical transformations affect y, and the horizontal transformations affect x. So the y values are going to get mirrored over the x-axis, so they become the opposite sign. And the x values, because we're shifting right, we're going to add 5 to all of those x values. So going back to those ordered pairs that I had, let's write down those ordered pairs. And my whiteboard is acting a little bit crazy today. So my ordered pairs are -2, 9, -1 and a third, 0, 1, 1, 3, and 2, 9. And following our transformations, all of the y values are going to become the opposite. That's what the reflection would do. It would mirror it over the x-axis. So all of the y coordinates have the opposite sign. And all of the x coordinates we're going to add 5 to. So -2 plus 5 would be 3. -1 plus 5 would be 4. 0 plus 5 would be 5. 5 plus 1 would be 6. And 2 plus 5 would be 7. So these are my new ordered pairs with the transformation. So let's see what that graph looks like. With my new ordered pairs, I have 3 and -1/9, 4 and -1/3, 5 and -1, and 6 and -3, and 7 and -9. So I can connect these points together. You can see that the horizontal asymptote has not moved. It is still right on top of our x-axis. We have that horizontal asymptote at y equals 0. And we also need to know the y-intercept. So this I'm going to do by calculation. Our f of x was -3 to the x minus 5. I'm going to substitute a 0 to find the y-intercept. That would be -3 to the 0 minus 5. That's -3 to the -5. And that's -1/3 to the 5th. Let's see what 3 to the 5th is. I know that 3 to the 4th is 81. And 3 to the 5th would be 243. So that's -1/243 for my y-intercept. Thank you for checking out my videos. Have a great day.